I have now shown you everything necessary to prove the hockey stick identity. And this is actually like the sixth time I've tried recording this video because this is actually pretty difficult to prove without making minor errors that I don't want to show up on a YouTube video. It's actually not that bad, but there's a lot of indices involved, so hopefully you're ready to go along for the ride with me because I think I can do a good job presenting it. So last time we saw that there's this identity called the hockey stick identity where if we draw a figure on Pascal's triangle that looks like this, the sum of these guys, 1 plus 2 plus 3, should equal 6. And this will work for any arbitrary hockey stick that you draw along the triangle. And it will maintain equivalence. This is the formal way of writing down the identity. Let's go down, let's explain why this is how it should be written mathematically. As we saw in the last video, is that Pascal's triangle is really just a bunch of binomials in a tree disguised. So this guy has the same, I could draw an equivalent stick by drawing this guy. So it should be the case that 1 choose 1 plus 2 choose 1 plus 3 choose 1 should equal 4 choose 2. And this looks like the formula applied, but the only thing that's missing is the j equals 0 index. But that's okay, we can actually tack that on because 0 choose 1 is 0. Because I have a lower number up top than I have in the bottom, as I showed in the last video. You can't choose one object from a pool of 0 objects. So it's okay to tack on these extra terms because they're all just going to end up being 0. Okay, let's prove this guy. We're going to start with geometric series. You could prove this with induction, but this is actually a more interesting way of proving the identity. So recall, if you haven't seen this, I'll link it in the description. I have another video called 0.9 repeating is more interesting than you think. And I actually derive the formula for the geometric series. But you can just take it for granted that x to the 0 plus x to the 1 plus x squared plus x cubed plus all the way to x to the n can be written as x to the n plus 1 minus 1 over x to the n. I'm sorry, x minus 1. This is the shortcut way of adding this geometric series. This is what this is on the left-hand side. This is called a geometric series. We'll begin the proof by making the substitution x equals t plus 1. If I make this substitution, this will turn in, the left-hand side will turn into t plus 1 to the 0 plus t plus 1 to the 1 plus t plus 2, t plus 1 squared all the way to t plus 1 to the n equals t plus 1 to the n plus 1 minus 1 over t plus 1 minus 1. And this denominator will just simplify to t. Okay, well, how is this helpful? Well, let's apply the binomial theorem to each term. This is a form of a binomial, so let's do it. This term becomes the sum from j equals 0 to 0 of 0 choose j times t to the j. Plus, this term becomes the sum from j equals 0 to 1 of 1 choose j times t to the j. You can keep going with this. You'll get the sum from j equals 0 to n, this is the last term, times n of n choose j times t to the j. And on the right-hand side, I'll do it in a different color, and I'm also going to not use j this time. You'll see why in a moment. This term becomes the sum from k equals 0 to n plus 1 times n plus 1 choose k times t to the k, all of that minus 1 over t. And I'm going to simplify this right-hand side. So let's look at the sum from k equals 0 to n plus 1 times of n plus 1 choose k times t to the k. I'm going to take out the 0 term here. The 0 term is going to be n plus 1 choose 0 times t to the 0. And then I have to add the rest of the indices, so that would be the sum from k equals 1, because I took out the 0 index, to the n plus 1 of n plus 1 choose k times t to the k. Okay, well this guy, t to the 0 is just 1. And n plus 1 choose 0, what is n plus 1 choose 0? I'm going to do this off to the side. This off over here. What is n plus 1 choose 0? Well, that is n plus 1 factorial over n plus 1 minus 0 factorial times 0 factorial. Well, 0 factorial is 1. N plus 1 minus 0 factorial is n plus 1 factorial. So what you're left with is n plus 1 factorial over n plus 1 factorial, which is 1. So n plus 1 choose 0 is 1. Okay, and I'm also going to simplify this guy. I'm going to make a substitution of the index. I'm going to let j equal k minus 1. If I do that, then this k equals 1 is going to change. When k equals 1, j equals 1 minus 1, which is 0. So the new sum is going to start from j equals 0. This upper index, it's going to, when k equals n plus 1, j is going to equal n plus 1 minus 1, which is n. So the new sum is going to go to n. Okay, I'm not going to change this n plus 1 because this is just a constant inside of the sum. But this k is going to change. So if j equals k plus 1, that means that k equals j plus 1. So this guy right here is going to change to a j plus 1. And this t to the k likewise is going to change to a t to the j plus 1. And it looks like this whole thing simplifies, let me change color. I shouldn't be using all this blue, is 1 plus the sum from j equals 0 to n of n plus 1 choose j plus 1 times t to the j plus 1. Okay, let's substitute that back. See, I've been messing with this guy the whole time. Let's substitute this guy back into this part of the equation. So I'm going to get the left-hand side. I'll actually just rewrite the left-hand side. Left-hand side was the sum from j equals 0 to 0 of 0 choose j times t to the j plus the sum from j equals 0 to 1 of 1 choose j times t to the j plus ... the sum from j equals 0 to n. I'm really hoping I don't make an error because I don't want to do this video again. Like I said, this is like take 6 of n choose j times t to the j equals, okay, let's plug this guy in. Let's plug this guy into this part of the equation, our right-hand side. 1 plus the sum from j equals 0 to n of n plus 1 choose j plus 1 of t times t to the j plus 1 minus 1. This minus 1 comes from this guy. All of that over t. Great. Okay, so what's going to happen is this one is going to cancel with this negative 1, and we can actually put this t inside of here, and that will reduce the exponent on this guy to just j. So this will now be the sum from j equals 0 to n of n plus 1 choose j plus 1 times t to the j plus 1. Actually, that needs to be rewritten as just j, not j plus 1, because we put this t in there and now we have this. Now we have just this on the right-hand side, and we're almost there. So what we need to recognize is that this is a polynomial in t. So it's a polynomial in t. T is the variable, and there's a t to the 0 term in here, that's the minimum, and then there's also a t to the n term because you get to this index. So this is a polynomial in t of degree n. And so is this guy, because this t is also just a variable here, and it goes from degree 0 to n. So it's a polynomial of degree n. So in order for these two things to be equal, the coefficients on the t to the whatever term has to be the same. So let's just think about what is the coefficient of the t to the m term. Well, the coefficient on the t to the m term is going to be, from the left-hand side, the only places you're going to see a t to the m, and this is just some arbitrary m, is going to be the sum. The contribution to the t to the m term is going to be, from this side, from this guy, is going to be 0 choose m. 0 choose m times t to the m. Of course, it never gets there, but forget about that for now, because if this was higher than m, then if this is higher than m, then it's just going to be 0, so we can include it anyways. And the contribution from this term right here is going to be 1 choose m times t to the m. And this is going to keep going. And the contribution from this guy is going to be n choose m times t to the m. That will be the contributions to this coefficient from each of these guys. Well, because these polynomials are equivalent, that must equal the contribution from this guy. And what is the contribution from here? Well, it would be the t to the m term. And the t to the m term happens when j equals m. So we can substitute an m here. We'll get n plus 1, choose m plus 1. And we're almost done. We're very close. Just divide both sides by t to the m. We don't even need that anymore. And look what we end up with. The sum from j equals 0 to n of j choose m, which is exactly what I have written down here, is equal to this guy, n plus 1 choose m plus 1. And that is the hockey stick identity, UED. And now, using this identity, what was the purpose of this? Why did I show you this? The reason I showed you this is because we're actually going to come up with a formula using this identity of what 1 squared plus 2 squared plus 3 squared plus ... plus n squared is. There is a formula for this, I'll call it sigma 2 of n, that you can prove what the formula is using this identity. And I'll do that in the next video. Thanks for watching.